So let me just start with some administrativia. The first thing is, of course, this is the Logic CS245, but that's the enriched version. The enriched version means that we will be going faster than the usual course, and we will cover more topics, and the mathematical level of this course will be higher. So this is for students who enjoy mathematics, who would like to be challenged. I mean, the Logic course is a very big course. We teach it to lots of students. There's heterogeneity in the students. So we decided that it's worthwhile to have one section for students that really enjoy it. So, I mean, you're all welcome to start. I think that formally you are allowed to fall back to the usual track within the first 2 weeks. So I will try to give you a feeling of how it's going to be within the first 2 weeks. If it happens later, then I will make an effort to still allow you a smooth transition to the usual track of the course. But in any case, this is going to be more demanding, at least mathematically, intellectually, than the usual course. Not more demanding in terms of the amount of homework assignments that you need to do. Okay, so that's the basic. So my name is Shai Ben David. And I did my PhD in mathematical logic many years ago, but that still feels to me like my mother tongue, mathematical logic. So I really enjoy it. But over the years, I've turned into being more and more practical, and now my main research is machine learning, which is another course that I'm teaching. But I think it's a beautiful topic. So I hope that I'll be able to share my enthusiasm with you. I guess the most important question that people ask right away is, what is the mark composition? So it's going to be made of 3 parts. There's going to be assignments, roughly bi-weekly, and there will be 30%. And there's going to be a midterm. And the midterm is very important because my experience is that students in my classes, they feel that it's very nice and easy and logical when I'm talking, but then when it comes to the exam, it turns out that there is some kind of misperception, and it's harder than people thought. So the midterm is kind of a wake-up call. So the midterm is going to be 30%, but it is going to be 30% only if it's better than the final. If it's worse than the final, it doesn't hurt you. So it can only help you, it cannot hurt you. And then the final is 40%. So this is either 30% or 0. This is either 40% or 70%, according to whichever combination is better for each of you. We have 2 TAs, and we will have a website soon. We'll have a Learn website. We have 2 TAs. So one is Aaron. I have to look at my spelling for the last names. Volker. And the other one is Hamide. And even more complicated last name, something like this. But on the website you will have their names and their office hours and their email addresses. My office is DC 1311, and I'll have office hours weekly on Wednesdays at 2 to 3. My email is shai@uwaterloo. What else? We are going to have video recordings of the course. I'm going to have a dedicated YouTube channel for the lectures of this course. And usually there will be up within a week of the lecture. So within a week, you will be able to just view the video and go over the lecture if you wish. So there's going to be the video recordings. And we have the textbook. And I chose a textbook that is pretty advanced. It's a very good book. It describes things. It explains very nicely, very precise. But it is also a bit advanced. And the author is Anderton. And the book is called Mathematical Introduction to Logic. And it covers a little bit more than what we are going to cover in the course. Am I missing anything important? Any questions so far about this? Yes?
Is the textbook necessary or just like an additional thing to help?
It's an additional thing to help. You will have the video lectures. If anybody wants to take notes and send me notes that we can upload, I'll also be happy to, although I don't feel it's very necessary since we have the videos. But if anybody sends me good notes, you will get extra bonus points for it. Which reminds me that policy for bonus points, I really want to encourage question discussions and so on. So anybody who catches me making a mistake, not a spelling mistake, I'll make a lot of those, but a mistake in the content, raise your hand, tell me, and you get 1 extra point in the final grade of the course. So if you catch 100 mistakes, you don't have to do anything else in the course. If you think that something is a mistake and you raise your hand and point to it, and it's not a mistake, then I will just ignore it and you will be protected by anonymity. So there is no penalty to making comments which turned out not to be correct. Also, if you feel that you don't understand something and want to ask, never hesitate. I mean, you are not, if you ask a question, you didn't understand something, it is usually the case that 20 other students also didn't understand it and they will appreciate that you ask. And so really don't feel like I'm the only one who didn't understand, so why should I bother everybody? Do bother everybody. Probably there are 10 other students that feel exactly the same and I'll be grateful for your question. So ask questions, even if you're just not understanding my handwriting. And I would really like to encourage discussion. I kind of believe that you are all extremely smart and enthusiastic about your studies, so I look forward to the interaction. I have great experience with, I've been teaching here for 11 years now, and my experience is that we really have some of the greatest students on earth. I mean, we really have very talented students, but also there are students that are struggling. So there's a lot of heterogeneity, and I hope that this class will be students that are finding it too difficult will just smoothly slide back to the regular option, and there's no cost to it. Okay, any questions so far? So let me start by saying what is the goal of the course. So first of all, to place the course belongs to computer science theory. So it is, or the mathematical foundations of computer science. So it is really a theoretical course. There's going to be no programming, and I do not see any conceivable startup that will make you a millionaire based on this course. And I don't recall any such a case in the past. So this is for people who like theory. It is a mathematical course, but it is math with lots of applications. It's mathematical, but with lots of applications to computer science. When I'm teaching, I mean, I have my goals that are some, so the goals, I can say, roughly divide them to 3 groups. One of them is there are some concrete skills that you need to acquire. So, for example, how to distinguish between a statement that says for every x there is a y such that x is greater than y, to for every there exists an x such that for every y x is greater than y. So don't confuse order of for all and exists. Or be able to translate English sentences into a mathematical formal statement and so on. So there are few skills, few concrete skills that we will all need to learn. The other goal is more conceptual. So logic has a very clear, it's kind of the basis of mathematics, and it's about how to reason formally and how to do reasoning in a precise and how should I say, correct manner. And so this conceptual idea is one of the goals of the course, that at the end of the course you will be better at seeing what is a well-defined mathematical definition, what is a correct proof, and so on. And the third is that there are some really beautiful insights. Of course, beautiful to people who appreciate this kind of intellectual game. So I think the most striking things that we will see is the undecidability of certain tasks. So there are certain tasks that no computer program can carry out, although they are fully defined mathematically. So we need kind of a logical reasoning to show it. And the other very striking result is Gödel's incompleteness theorem that says that there are statements that we can neither prove that they are show that they are correct, nor can we show that they are wrong. But we will get to it later. Okay, so these are our next, I mean, in increasing order of abstractness, this is what we're going to do in the course. So, let me start with what is logic. So, what is logic? And in some way, it is also an abstraction of what is mathematics. And the main thing to realize is that logic is not about figuring out what is true and what is false. It is not about distinguishing truth from false. It is about, it focuses, it's all about on how to reliably get from assumptions to conclusions. So it is not about the question of whether things are wrong or right. So you see, if I look at something like F equals ma, like Newton's basic law for the connection between power and mass and acceleration, the question of whether this is true or false is a question for people who are doing physics. It's not a question for logicians. The question for mathematicians, so this is physics, if it's true or not. Mathematicians can can ask, okay, if f equals ma, then a equals f חלקי divided by m. So this is kind of a mathematical statement. If this is true, then this is true. The mathematician doesn't concern himself with whether this is true or not. This is something that lives in the world, and we don't care about the world. We just care about our intellectual activity. So this is kind of irrelevant to us. The mathematicians can show you this. The logician can take another step of abstraction and say, oh, I'm not so sure about that. What I am sure about is that if whenever x equals y times z, then y equals x over z, then if that is the case, or if f equals ma, then a equals f divided by m. So we take higher level of abstraction. We ask ourselves, what are our way of reasoning based on? And so, does it make sense what I'm saying here? Okay. Oh yeah, I mean, we have this thing here. What I'm saying here is that you can say even this implication, if f equals ma, then a equals f over m, can be questioned. And if I want to substantiate it, I can be more careful and say, I know it is true if it is indeed the case that whenever x equals y times z, then y equals x over z. If this rule holds, then I can say that from this I can conclude this. So in logic, we're kind of going to the higher levels of abstraction, and we want to understand how to reliably reach conclusions from assumptions. And we don't ask the question of what is true and what is false. So let me start as an example by probably the most famous logical argument. So I think it deserves being called the most famous logical argument is due to, how do you say it in English, Socrates? Okay, and he said he was one of the first logicians that we know about, and he did the following very pessimistic reasoning. He says, if all men are mortal and I am a man, then, now a very sad conclusion, I am mortal. Right? So this is a very good example of a logical reasoning because it's up to the biologist to figure out whether all men are mortal or not. But the logician's role is to say, if we make these two assumptions, then we get to this conclusion. So logic is about doing those things reliably. And I think that the first reaction that you get when I show you this is that I don't need to go to university for this. I mean, if I ask you, I give you another example, and I tell you that if all crows are black and Tweety is black, then Tweety is a crow, and I will ask you, is this a valid way of drawing conclusions from assumptions? And you will all tell me no, because we're not all smart enough to distinguish this kind of valid implication from this invalid implication. So why do we need logic? I mean, maybe we don't need to learn it. Maybe common sense is enough, and if you're smart enough, we have this common sense. And if you're not smart enough, then nothing will help. So what is the point? So turns out that things, sure, on such a simple level, things are very straightforward, but they can get more complicated. So it turns out that if we just rely on our common sense, we can get ourselves into trouble. So here are some few examples. I think one of the most influential examples is called the Russell's paradox. And the Russell paradox, yes?
Not actually a mathematical mistake, but that was actually Aristotle that said that.
Oh.
It was Aristotle talking about Socrates when Socrates was being executed.
Oh, that's really interesting. Okay. That's really interesting. It deserves the bonus point. Send me an email, I'll check it, and if it's true, you'll get the point. Very interesting, because I've been teaching it for, I don't know how, I don't want to embarrass myself for how many tens of years I've been teaching it, and nobody complained so far. So.
Also, the Russell you're referring to has two L's.
Oh, he has two L's. Okay. Okay, Russell's paradox. Okay, so what's the Russell's paradox? Russell's paradox is also called sometimes the Barber paradox. So assume that there is a very remote, isolated village, and in this village there is only one barber, and this barber shaves everybody in the village that doesn't shave themselves. So nobody grows a beard in this village, and the barber shaves. The barber in the village shaves every morning, every man in the village that does not shave themselves. And nobody grows a beard. So what's wrong with this statement is they can ask, does the barber shave himself? And you can easily see that we get into a contradiction, because if he shaves himself, then he's one of those that the barber doesn't shave. So he should not shave himself. But if he doesn't shave himself, then he's not one of those that shave themselves. So the barber should shave them.
But the barber does shave. But when the barber shaves himself. Okay.
Okay, let me give you, I mean, this one is, it's a very famous paradox, and the interesting thing is it has really led to some revolution in mathematical logic. It kind of alerted mathematicians to the need for some more formal basis for mathematical logic. So it did have a real influence, although it's such a simple paradox. And I can show you just for fun a couple of other paradoxes, but here is another one that sounds, I mean, this is kind of, very easy to resolve this. What is the answer to this paradox? Why it's not a paradox? Yes. What? There's no such barber, there's no such village. How do I know that there's no such village? Because this is a proof of contradiction. If there was such a village, then we got a contradiction. So therefore, I have a proof that no such village exists. But so let me show you another one that really looks mathematical. That really looks like, I'm sure that many of you have seen the proof that there are infinitely many prime numbers. Right? And one of the proofs that infinitely many prime numbers, you say, assume that there were only finitely many of them, then take the product of all these finitely many prime numbers and add 1, and this number would be divisible by something which is not among those primes. So now we have a paradox which has the very similar flavor of argument, and this is called Berry's paradox. And Berry's paradox talks about the following concept, and it's the concept of numbers that can be described in words. So the question, so we are talking about the concept of numbers that can be precisely described by an English sentence. So we can talk about, say, of course, the number 10 or the number 10 to the power 10, and we can also describe the number of hair on the heads of all students in this class, and so on. There are lots of numbers that I can describe by an English sentence, and they can be very, very big. But I want a description that gives me a precise definition of a number. Okay, so these are the concepts that we are concerned about. And now we want to, I mean, of course, we can cheat. I mean, I want to describe the number so I can say, okay, here is the description by an English sentence, is the number whose digits are 7, 5, 3, 2, and so on. So to make it interesting, we will put one more limitation, and we will say described by an English sentence of at most 100 characters. So we are concerned with numbers. So let's say B be the set of all numbers that can be described by an English sentence of at most, say, 200 characters. And I'm talking about integers, rational numbers. Okay, so it's a well-defined object. And now I'm asking you the following question. Is B a finite set? What do you think? It shouldn't be difficult to. Why do you think it's finite?
Because there's finitely many combinations of characters.
Right. So the answer should be yes, because there are, I don't know how many characters, 26 or 26 characters. So there are at most, yes, since there are at most 26 to the power 200 such combinations of characters, and each combination of English characters describes at most one number. So the number of the set of numbers that I describe is definitely smaller than the set of all such combinations, and there are so many such combinations. So far, it looks like everything is reasonably nice. So where's the paradox? Yes?
What if you just get a pile of stuff and say that many? And then when they add one more number, you just put one more thing in the pile.
So, but you have to describe it. You cannot just say, I mean, look at this pile. I mean, describe the pile to me. Yes.
The number that is 1 more than the biggest number in B.
Right. So since B is finite, it's well defined, is the set of all numbers that can be defined by at most. So we can look at the number which is described as following. The first number that cannot be described by an English sentence of at most 200 characters. Now, if B is finite, as we argued, then of course there is the first number which is not in B. For every finite set of numbers, there is the first number which is not in the set. So if B is finite, then this is a valid description of a number. It is a well-defined number, the first number which is not in B. But now, can this number be described or not? I mean, I just described it with an English sentence of at most 200 characters. But then, if I describe it, then it's not a number that I meant to, because I meant the one that cannot be described. Yes?
So, yeah, it's like you're assuming that B exists even if you haven't used up all the characters to define it. Like,
What do you mean use all?
like if you were to just actually use up all the characters to in B, like actually use them.
What I'm doing is I'm looking at, you can think of it this way. You look at all combinations, like order them by dictionary order. All combinations of at most 200 characters. First, all combinations of 1 character, then 2, then 3, and you go by dictionary order. Okay? And now you go over this long list, and for each of them, you just cross it out if it's not an English sentence, if it's not a valid English sentence, or if it does not uniquely describe a number. So you go over this list and cross out things. Now you are left with still quite a big list that contains all of those guys like the number 10, 10 to the power 10, the number of students in this class, and so on. So this is your set B. So everything is well defined and nice. But it's finite. Since it's finite, there is the first number which is not there. Right? So now suddenly I gave you a description in the list of, so is this, we got a contradiction here. Anyway, I don't want to get so much into analyzing these contradictions. What I wanted to do is just to alert your attention that although intuitively we think that our common sense can resolve any logical issue, any question of how to get from assumptions to conclusions, there are things that easily confuse us. And the problem becomes more and more complicated when we talk about complicated arguments like mathematical proofs or computer programs. If you want to reason that a computer program does something, can we just rely on our common sense? Will we be smart enough not to fall into one of those traps? Okay, so maybe one more simple, there are lots of paradoxes. So let me show you just one more. And this one is actually of practical value. So what's your name? You. No. You.
Alexander.
Oh, yeah?
Alexander.
Oh, that's difficult. Alex, okay. Okay, so now I'm going to prove to you that Alex is going to become a millionaire by the time he's 25 years old.
But he's 30.
No. You're not 25 yet, right? Okay, so that is going to be very... So I'm going to have 2 sentences in this box. And one is saying at least one of the statements in this box is false. And the second one is Alex is not going to be a millionaire by the age of 25. Okay? Now, what I'm claiming is that this statement is true. Why is this statement true?
The other one will be false.
What? Because if it's false, then it's true. If this one is false, then at least one of the two statements in the box is false. So this is exactly what it was saying. So if it's false, it's true. So this one must be true. Okay, so now we know that this statement is true. So we know that one of these two statements is false. So it must be that the second one is false. So congratulations. Okay, so I was just trying to loosely convince you that we cannot completely rely on our common sense in order to distinguish valid ways of deriving conclusions from invalid ones. So now we are kind of slightly motivated towards the task of logic. So the task of logic is really to investigate how to get from assumptions to conclusions in a reliable manner. And it turns out that the first thing we need to do just want to make sure that I didn't forget anything. Okay, so the first thing that we need to, the goal is to develop reliable tools for going from assumptions to implied conclusions. And it turns out that in order to do so, we have to focus on the language that we use. So it's very important to, so the first observation in this road, in this journey, is that we should not rely on any natural language for that purpose. And what do I mean not rely on? It turns out that the language that we use, like English, contains kind of fallacies that are very difficult to detect, and it's just because of ambiguities of the language. So let me give you, I'll show you more examples in the assignment, but let me give you just one example of why we have to kind of do something different than use English language for formal methods. So let me prove to you that McDonald's hamburger is better than eternal happiness. So, I mean, you didn't know it, right? I'm being paid for advertising McDonald's hamburger. So here is the proof. So first of all, nothing is better than eternal happiness. I mean, you can replace it by whatever you think is the most important thing in life. And on the other hand, a McDonald's hamburger is better than nothing. So now, by transitivity, McDonald's hamburger is better than nothing. Nothing is better than eternal happiness. So the McDonald's hamburger is better than the eternal happiness. And the problem here is not that, so we have here, right? So we have the McDonald's hamburger, which is better than nothing, which is better than eternal happiness. And the fallacy is not that better than is not transitive. Better than is transitive. Is A is better than B, and B is better than C, then A is better than C. That's not where things go wrong. Things go wrong by our use of English language. And there are lots and lots of such things. And actually, even the paradox that I showed you before, the Berry paradox with a set of all things that can be described in at most 200 characters, it has to do with the fallacies of language, because I didn't fully define what do I mean by describe. What is the language that I'm allowing myself to use? Okay, so we want to get away from natural languages, and actually the course and the logic is really about one of the central themes in logic is really constructing formal languages. So logic is a lot about constructing and then analyzing, of course, because that's what we want to do, formal languages. And we want to have reliable tools for getting from assumptions to conclusions. We cannot rely on natural language, therefore we have to come up with a formal language. I mean, formal language is something you all know about. Any programming language is a formal language, right? It's a language which is just defined by rules. It's not a natural language. We need formal languages for reasoning about assumptions and conclusions. And what we're going to do in this course, we are basically going to talk about two formal languages, maybe about the third one as well. So we are going to talk about, we will focus on two such languages. The first one is called propositional logic. Or PL. And propositional logic is the language in which you can say things like P or Q implies S, or things like this. So it is a very simple language. It has variables, it has or and implies, and very simple language. The language is simple, and therefore, I mean, it looks like, and actually, I mean, it looks like there's nothing to do with this language, but I like very much to focus in the course on this language. And the reason is that it is so simple technically that we can really focus on the important issues of logic rather than worry about the technicalities of language. So this is my personal take. The book that I recommend to you almost says nothing about this. They kind of assume this is too simple to discuss. And but we will devote about half of the course to this language, just because I think it's a good playground or a sandbox to demonstrate what is being done in logic. And the other language that we're going to talk about is what is called first order logic. And first order logic is much more useful and can express a lot of things. So this is the language that on top of this, it has quantifiers for all and there is. So it can say things for every x there exists a y such that x, say y is greater than x. Things like that. And we can combine it with ors and ands and implications and so on. Okay, so I mean, we're not getting into this. So this logic, the first order logic, is a logic that is believed to be able to express every mathematical statement, so it's a very potent logic. But the downside is that it's also very technical. So I will get to it because it's important. We will spend significant amount of time on this logic, but also only after we kind of get the principles from analyzing the simple language. And on top of it, we will maybe talk about some other logics as well. So there are notions that are really relevant to computer science, like temporal logic. So temporal logics are logics that allow you to talk about time. So you can say things, if there is a request, then there is eventually be reply to the request. So when I have to say eventually, I'm talking about the run of time. It's called temporal logic, and it allows me to reason about behaviors of programs or things like that. So we will also get to talk about temporal logics and maybe other logics as time will permit. But the first part of the course will be the propositional logic, just to get the principles of what do we do when we do logic. Okay. So I'm just setting up the ground for our discussion. And to start, we want to define this language. Now, whenever we define a language, this is one of the major themes of the course. Whenever we define a language, we are going to distinguish between two components of the language. An important distinction when we talk about a formal language is between the syntax versus semantics. So by syntax, we mean the rules that allow you to write correct sentences. So when you do programming, syntax is kind of what are the rules that you're allowed to, what consists a valid program. It's what the compiler checks as soon as you give it the program. It checks that you have, I don't know, enough ends and beginnings and definitions of symbols and so on. So syntax is kind of the formal definition of what is valid in the language. Everything that we can do without attaching any meaning. So this is just we can say it's the form of the language, and the semantics is the meaning of the language. So if I draw something like this on the board, then this is a table, but the semantics is this guy. The syntax is a word with 5 letters. Let's start with T and end with E. And all of this is discussion about the syntax. It has 5 letters, starts with T, ends with E, I don't know what. The semantics is that it is this guy, and so on. So this distinction, when we just speak natural language, we very often don't worry about, are not aware of this distinction. But when we come to a formal language, it becomes very crucial to talk about this distinction. So this is going to be an important theme in the course, all the time distinguishing and comparing what can we learn from one about the other. So we start with propositional logic, and we start with the syntax of propositional logic. The syntax of propositional logic. And what we wish to do first is to try to define the set of all valid words in this language. So I want to define the set of all words of this form. And we want to be very formal about our definition because this is exactly the reason why we are switching from a natural language to a formal language. So why is this a problem? It is a problem because this set of all formal words in this language, a set of all propositions, is an infinite set. So we want to define it precisely. So I want to take a kind of a step aside and ask, what tools do we have? So this is an infinite set. What tools do we have for formally or precisely defining a set? So if I want to define some set, say the set of all students in this class, what tools do I have to define it in a well-defined way so that everybody will be able to check whether it belongs to this set or does not belong to the set? So what's the simple way, if I want to know who are the students in my class, what's the simplest way for defining it? Yes?
Listed.
Right. So the first tool is just make a list of all members of the set. However, there is a downside to this. This is very precise, very nice, no worries about it, but there is a problem. And the problem is that if the set is infinite, it's very difficult to make the list. So if I want now to describe, say, the set of all even numbers, so I can try to make a list. Set of all even numbers, I can say 0, 2, 4, da, da, da. But that's not a precise definition. So what other ways I have? How do I define the set of all even numbers? Yes?
You can describe a common characteristic between.
Right. So the second tool is to describe a common characteristic. So by a common characteristic, say numbers that are divisible by 2. That's a common characteristic. That's a very useful way of describing a set. But turns out that even this tool is sometimes not flexible enough. I want to describe sometimes sets for which I'm not aware of any common characteristics. So let me give you an example of sets that are well defined, but I cannot describe them by common characteristics. Yes?
But before we do that, I don't think these two are enough to define even numbers. Because you can only get finite sets from the first one and smaller sets from the second one. So how do you get it?
I'm not.
Okay, from the first one, make a list. You only get finite sets.
Right. With a list, I can only define clearly finite sets. Right.
And from the second one, you can get from a set to a smaller set.
I have to start with some set. That's a good point. I have to start with some universe and define my set inside this universe. That's a very good point. And actually, I was ignoring this point so far, but let me take a note of it now. It's a good, very good comment. So we always assume that we have some universe of objects, and everything that we want to define are going to be a subset of this universe. And the universe is known to us, because otherwise we get into real trouble of defining what is our universe. That's what, logic addresses it, but in a much more advanced way. Right. So we assume that there is a universe. So here I assume that my universe is the universe of all natural numbers. And in the universe of all natural numbers, I wanted to define the subset of all even numbers, but I did assume that we know that we are talking about numbers. Okay, so my universe was natural numbers, and I wanted to define even numbers. I could do it. Now let us look at something different. I want to look at the universe of all people, of all human beings, and I want to define the subsets of all my blood relatives. So my universe is going to be all people, all human, and my subset is going to be my blood relatives. Now, the problem is that I don't know of any common property. I mean, I would like to think that all my blood relatives are smart, but I have this nephew that... Right. I would like to believe that all my blood relatives are good looking, but I also have counterexamples to this. So I do not have any common property to define them by. But still, it's a well-defined set. So I need a different method of defining. Also, I cannot list them because it can grow and grow and grow, and I don't know who is the wife of the cousin of my, so on. Yes?
When you assign your blood relative, first of all, if you begin to remove common characteristics, like you said, smart and good looking, then I'm trying to ask, what are you thinking in your mind when you're saying your blood relative?
That's exactly what you want to do. I mean, I want to give you a definition. Right. And the question is, can we come up with a definition that will feel that this really describes what we wanted to? Yes?
So we do this by defining an object and relationship between two objects?
Right, so you're going in the right direction. So what we are going to do is we're having a very useful tool for defining sets, and this is a definition of sets, or let me call it like inductive definition of sets. So what do I mean by inductive definitions? So let me start with the example of my relatives. So what I can do is I can start with some core set. I will start with some core set of people that I know that are blood relatives of myself. And I have one very good candidate to put in the core set, and that's me. I'm definitely a blood relative of myself, right? And then I'm going to have operations. So operations could be son of, daughter of, wife of, mother of, and so on. So I have here a finite set of operations. So this should be a finite set such that if X is a blood relative of mine and Y is obtained from X by one of these operations, Y is the son of X, and X is a blood relative of mine, then Y is also a blood relative of mine. And now the set of my blood relatives will be the smallest set that contains the core and is closed under this operation. So the set of my blood relatives is closed under this operation in the sense that if anybody is in the set and I apply one of these operations, the person that I get to is also a blood relative of mine. So now I define the set in a different way by these two components. One of them is a core set, and the other is a list of operations. So we want to, and this is going to be a very useful tool for defining sets, for defining infinite sets in mathematics, and in particular in logic. So let me try to formalize this tool. So I want to formalize this tool of inductive definition of sets. So an inductive definition of sets contains two components. So an inductive definition of a set consists of these components. One, I have some core set. Oh, let me even start one step before. I have some, this is in view of your comment, we start with some universe set. Every set that I define is going to be a subset of this universe. In our case, the universe was the set of all humans. And my blood relatives was a subset of this. Or the universe is a set of all numbers, and I define a subset of numbers. Then my second component, so let's call the universe set, let's call it X, and we often will not mention it. Then I have a core set, and a core set is some set A subset of X that I will define in any other way, and this is the set that I start with. Yes?
That definition of blood relative is not really the definition of blood relative, because it kind of infinitely up and down, so it would include like your brother's wife's mother, who really doesn't share any blood with you.
Okay, so yeah, maybe the words.
Even just parent and child will eventually get you all humans. When you
Yeah,
climb
all
back up to the-
humans with the exceptions of isolated populations.
Right. Okay. Maybe. I mean, it's really a question. I mean, this is a well-defined set. You can argue about whether this is what I meant or not. So if I'm asking who should I invite to my wedding, then this is probably a little bit too wide. But it's a valid definition. I just want to. Okay. So I have some universal sets, and I have a core set, which is what I call a core set. And my third component is a set of operations and what is going to be a set of operations operation for me is a function. So an operation, this means functions from x times x times x to some arity r to x. So why do I talk about arity? I could talk about functions from just from x to x. Because here, son of, daughter of, wife of is just operation that involves only one element. But I could also talk about an operation like the sum of two numbers. Maybe I want to talk about a set which is closed under the operation of taking sums. And then my operation has two components, x and y, and my operation will be x plus y. Okay, so I allow operations which are not necessarily one variable functions, but they can be multivariable functions. So I have a set of operations. I'll call it P. And we require that P is finite. And now I define a set. So I have, these are my components. I have a universe, I have a core set, and I have a set of operations. And now I need to define the notion of a closed set. So we say that B, subset of A, is closed under the operations in P if for every B1 to BR in B and some operation F in P, F of B1 to BR is also in B. So this is a definition that I assume that many of you have seen it before in mathematics, a closure of a set under operations. I can say that the set of even numbers is closed under addition. Because if I take two even numbers and I add them, the result is an even number. The set of odd numbers is not closed under addition. So I have a family of operations, and I define what does it mean for a set to be closed under the operations. Yes?
Yeah, should it be a subset of x?
B subset of x. Very good. Okay, so you see this is an easy bonus point. So you just email me and you get the bonus point. Very good. It's B subset of x, of course. Yeah. Okay, so now we can define our set. So our definition is the set. We want to define the inductive set. The set defined inductively from these components x, a, and p is denoted I of a and p, the inductive set defined by a and p. I usually assume that we all know what x we are talking about, and is defined as is the set, the smallest set, the smallest subset of x that contains A and is closed under P. So we defined what does it mean for a set to be closed. So IAP is the smallest subset of X that contains A and is closed under the operation in P. It looks a bit confusing, so let me switch to a few examples. Yes?
What's the word right before IAP?
Denoted. I denote it by IAP. No. Ted. IAP. Okay? So let me give you an example. A very simple example. Let x be the set of all real numbers. So x is the set of all real numbers. And let my set A contain just one number, and this is the number 5. And let my set P contain only one function, and it is the function that takes a number x, or say two functions. It takes x, function 1, f1, takes x to x plus 1, and function 2 takes x to x minus 1. So this is my set P contains two functions. And now I'm asking what is going to be IAP for this A and this P. What is the smallest subset of real numbers that contains the number 5 and it's closed under F1 and F2? Yeah. So IAP is just going to be the set of all integers. Right? So it's a set that has -2, -1, 0, 1, 2, and so on. It's the set of all integers. That was a very, yes?
How do we define smallest?
All right, very good. Very good question, excellent question. I was wondering whether I should do it today or in the next class. But since you asked, let me. I mean, you see, I still do not know you, and I don't know if am I running too fast. Do you need more examples, or can we? It's okay, can we? Okay. But complain if things are running out of control. So that's an excellent question. Who was it? Yeah. It's an excellent question. How do we know that such a smallest set exists, right? So does such smallest set always exist? And now for that, we can actually prove that the answer is yes. And I can actually, I can define this set in a way that shows you that it exists. I mean, based on the operation of set theory. So the set IAP, I can rewrite it instead of describing it in words. It is the intersection of the set of all B subset of X such that A is a subset of B and B is closed under P. So now this is a set theoretic notation. I have here a collection of sets. And what this denotes is the intersection of all of those sets. All of the elements that belong to each of those sets. So you definitely, I'm sure that you know what is the intersection of two sets. But I can also talk about the intersection of a collection of sets. Could be even infinite. It's all elements that belong to each and every member of this set. Right? So in brackets, just recall or note, if you haven't seen it before, that given a set, let's call it W, it's a collection of sets. The intersection of W is the set of all X's such that for every B in W, X belongs to B. It is all the elements that belong to every member of W. I assume that W is the collection of sets. So this is a set theoretic notation. It kind of extends the notion of intersecting two sets. I intersect the whole collection simultaneously. Okay? And now I claim is that intersections always exist. For every collection of sets, the intersection of those sets exists. It's just that all elements defined this way, all of the elements that belong to all of them. And I claim that this set satisfies my definition. So we have to check. We have to check that this set, this intersection, really satisfies the requirements to be IAP. And this is my way of proving that this minimal set really exists. Right? So why does the intersection satisfy the requirements of IAP, of defining IAP? So first of all, first claim is I claim that A is a member of this intersection of the set of all B's subset of X such that blah, blah, blah. Right, so if we call this set some collection W, A is a subset of this set. Why is A a subset of this set? I mean, we want to show that this set W contains A. And we want to show that it's closed under intersections. And then we want to show that it's the minimal set that contains A and closed under intersections. Right.
Sorry, back there, is B supposed to be a subset of W, or is it?
No, B is a member of W. W is a collection of sets.
Oh.
Here is the collection of all sets B's that satisfy some property, and I want you to be a member of each of them. I mean, this set theoretical notation is sometimes confusing me. So what I'm claiming is this set satisfies the following property. A is a subset of it. It is closed under the intersections. It is closed under the operations in P, and it is the minimal such set. So why is A a subset of this collection? To show it's a subset, I want to show you that every member of A belongs here. So I want to show you that if X belongs to A, then X belongs to each of these B's. But that's, of course, the case. If X belongs to A, each of those B's contain A, so X belongs to each of the B's, so X belongs to the intersection, right? Since X in A implies X in B for all B in my W. Because that was part of my definition of what are required for B. The second thing I want to show you is that this intersection is closed under the operations. And we are really running out of time. Okay, so I don't want to squeeze something at the last minute of the class, so we will show the remaining properties on Thursday. Yes?
The question of how would you prove that the set P actually exists?
Which set P?
Set P of
No, you are given a set P of operations, and you are giving a course set A. You assume that both exist. Now you want to show that IAP exists.
Oh, sorry, I was asking the wrong question. The question I was coming to ask is how do you know that the intersection is not a null set?
Could be a null set. It could be an empty set. You're coming to.